Okay, good morning, everyone. Lecture 5, second week is almost half done. Let's pick up where we stopped. Last class, we stopped at parallel resistors. Okay, REQ. Again, derivation is not important. What is important is that you understand this equation and more importantly, know how to apply it. Okay. So, say resistors in series add up, resistors in parallel, you add up the reciprocals and take the reciprocal again. You can have this equation in your equation sheets. It's absolutely fine. There are 3 points that I want to note. The first one, if you think about a series network of resistors, the resulting value of REQ is always larger than the largest resistor in that network. If you add 10 plus 20, you would get 30. 30 is larger than 20. 10 plus 20 plus 30 gives you 60. 60 is larger than 30. The resulting value is always going to be larger. It's intuitive. Our brain always knows this, so we don't use it to actually error check. But the same thing applies to a parallel network of resistances. If you have a parallel network, the resulting REQ will always be smaller than the smallest resistor in that network. If you have 10 and 20 in parallel, the REQ cannot be more than 10. And that is something that needs to be registered in your brain because it is an instant verification check for your answers. If the resulting value you obtain is larger than any resistor in the network, or the smallest resistor in that network, that means your answer is incorrect. And you need to verify your, you need to check your work. Okay. So REQ for a parallel network will always be smaller. Will always be smaller than the smallest resistor in that network. Doesn't matter what values you have. You could have like 20, 20, 20, 20, and then 10. The resulting value will always be smaller than 10. Again, that's something to keep in mind to verify your answers. Not even verify your answer. It's an instant, if it's not smaller, then your answer is incorrect. Okay, second point. And this comes straight from this equation right here. If you have two resistors in parallel, a shortcut calculation is that it would be a product of the two divided by the sum of the two, actually. So if you have two resistors in parallel, a shortcut way of calculating it is that is a product of the two divided by the sum of the two. And again, it simply comes from this equation right here. If you have two resistors in parallel, you have this equation 1 over R1 plus 1 over R2. When you solve it, when you solve this equation, the resulting answer is R1 times R2 divided by R1 plus R2. Now, more often than not, you would use your calculators to perform the calculation, so it would not matter. But if you're trying to, just do it in your head or trying to do it without a calculator, then it's a good thing to keep in mind. It's a product of the two divided by the sum of the two. And the third point to note is that if you have n number of resistors in a parallel network, and they all have the exact same value, with X ohm, same value. Then the resulting Req is simply X divided by N. If you have N number of resistors in parallel, all having the exact same value, X for instance, then the Req is simply X divided by N. 10 and 10 in parallel, simply 10 divided by 2, 5 ohms. 1 over 10 plus 1 over 10, reciprocal gives you 5. 20, 20, 20, 20, 20, 5 20 ohm resistors in parallel, 20 divided by 5. And you can try it out using the standard equation. It'll always be X over N. So it's a shortcut. Okay, it's just a shortcut, but it's something to keep in mind. Okay. So remember I said we build on circuit analysis techniques step by step, right? So we first learned about Ohm's law, KVL, KCL. Now we're learning about resistors in series, then resistors in parallel. We'll take those two building blocks and combine them together to solve for a larger circuit, which is basically a network of resistors which are in series and parallel. And you take this large network of resistances, reduce them down to one single resistance. And then again, the next step after this would be introducing a source in this network. And then we will apply Ohm's law to solve for currents and voltages. So let's take a look at circuit 1, circuit A. We want to find Req between these open terminals. Okay. You're measuring between these open terminals. Think of it as this. If you had a lab bench and you had a meter, you're trying to measure the resistance on that circuit, you're taking your meter and you're putting it across those open terminals. You're measuring the circuit across those open terminals. So when you want to do this measurement on paper, what we do is we start at the farthest end of the circuit and you move towards the front end. So we start at the farthest end and we reduce the circuit step by step until there's only one resistor remaining towards the open pair of terminals. So we start at the farthest end. What do we see? For A, what do we see? We have R4. R4 shares two terminals with R3 and with R2. So R4, R3, and R2 are all in parallel with each other. Okay. So as a first step, what I can do is this is R1, and I'm going to call this as R5. R5 is simply the parallel combination of R4, R3, and R2. Okay, R4, R3, and R2. So far, so good. We start at the farthest end and we move towards our measurement terminals. Farthest end is R4. The next one is R3. Next one is R2. And then, whenever I do a step like this, I simply label it the next number up. So you had 4 resistors in the circuit. I simply label it as R5. Then Req is simply R1 plus R5. Because they are in series and R1 and R5 share one terminal. The other two are not connected together. Make sense? REQ is equal to R1 plus R5. Okay. All right. So let's actually, before moving to B, there's one more point. The circuit right now, for all of these circuits, we are measuring on the left, right? It's a measurement terminal. What happens if you change the measurement terminals? So instead of measuring on the left, let's say we take the same circuit. Instead of measuring here on the left, we measure it here. What do we see? Absolutely. That answer is correct. So the answer is it would only be R2, R3, and R4. R1 is not part of the circuit anymore. And the reason is only one end of R1 is connected into the circuit. The other end of R1 is open. It's not connected to anything. And because it is not connected to anything, it is an open circuit. It's a dead end street. You cannot drive a vehicle through there. A current cannot flow through R1. And if current cannot flow through, it is no longer part of the circuit. So looking at it from the other end, R1 is not part of the circuit. Yes. It's, yeah, if you're measuring from the right side, yes. So the point I'm trying to make here is that your circuit measurement would change depending on your change in measurement terminals. Okay. So again, REQ as measured from the right would mean that R1 is no longer part of the circuit. It may as well not exist. It's not part of the circuit. The farthest end moving towards REQ would simply be R2, R3, and R4. And they would just be in parallel. So REQ would be R2 in parallel with R3 in parallel with R4. Yes. Oh, you mean this? Oh, that's just my way of writing it's parallel. So yeah, two parallel lines, I'm just using it to write parallel. Yeah, because in textbooks, they have formatting. They have two parallel lines like this to note parallel. But if you write it out, it more often than not looks like the number 11. So I don't tend to use it. So it's, slanted. No, this is just shorthand that I use. I don't know if it's universal or not. Again, as I said, in books and articles, I've seen like two straight lines. But, in a book, you can easily differentiate between the number 11 and, that notation. Okay. So C is straightforward, so I won't cover it now in class. How about B and D? What do you see about B? In B, I have REQ measuring from the right. From the left. I start at the farthest end, which is R4, and I move towards the front. R4 is connected at the top. One end of R4 is connected to R2 and R3. which is this node right here. Okay, it's connected to R2 and R3. Then the other end of R4 is also connected to R3. So what can we say about the relationship between R4 and R3? They're in parallel because both of their respective terminals are connected together. And I will draw this out in a way that makes sense to me. So when I see a resistor on a diagonal, what I like to do is I stretch out that node to either make the resistor horizontal or to make it vertical. In this case, it makes sense to actually make R3 vertical like this. And so what I'm going to do is R1, R2, and then R3. I'm going to take this node and I'm going to stretch it out like this. And so R3 is now here. And then R4. Think over it. Let me know if you have any questions. Does it make sense? Okay. So then at this point, you can simply state R3 R4 is in parallel with R3. That parallel combination would be in series with R2. And that entire thing is in parallel with R1. Yes. So here, remember, in order for two resistors or two components to be in series, only one terminal has to be connected together. The other two terminals have to be open. For two components to be in parallel, both of their terminals have to be connected together. And so here, when I see R3, the question being asked is, how do I know whether R3 and R4 are in parallel? Without modifying the circuit schematic, R3 has terminals here. R3 and R4 terminals are here. And so if I look at R4 and R3, they are connected together here at the top right. And R4, keep in mind, this is a wire, so it's the exact same junction, is connected to R3. So both of their terminals are connected to each other. And that's how I can conclude that both of them are in parallel. Does that make sense? Right? Both of their terminals are connected together without a break in the middle or without any other component being connected together. Okay, then for C, it's the exact same thing. This time, instead of going towards the right, I'm going to take this node and I'm going to pull it towards the left so that R3 becomes vertical. And so R3 is now vertical, then I have R1 and R2 in their own place. Start at the farthest end. In this case, if you look at R1 and R2, they are connected together at one junction and one junction only. There is no third element at that junction. So at this junction, there's only two elements connected together. There's nothing else. And so we can conclude R1 and R2 are in series. Hence, we can write R1 plus R2. And then R1 plus R2 is in parallel with R3. Make sense, everyone? Any questions? Any questions at all? Okay. Again, the reason I take this slowly at the beginning of the quarter is because we are building step by step. And then next slide will introduce a next step. Students need to become very familiar with these techniques so that they can do this quickly, efficiently, and correctly. So we learned about resistors in series, in parallel. We combined both of those together. We learned about reducing a large network of resistances down to one single network. Now we introduce a source, a voltage and a current source into this network. And we define a technique or introduce a technique called series parallel equivalence. Okay, series parallel equivalence. So in this circuit, we have a bunch of resistors and we are given a source. In this case, the source is a voltage source. Our job is to figure out the voltages and currents that appear in the circuit. And in this case, we have three resistors, R1, R2, R3. So we need to figure out the voltages and currents for the three resistors in that circuit. Steps are pretty simple. It's a three-step technique. We reduce, we apply, and then we expand. Okay. We reduce that network of resistors down to one single resistance. We apply Ohm's law, and we calculate the third quantity, whether it's current or voltage, does not matter. And then we expand the circuit back up again in the reverse order. So first thing to do is we remove the source from the circuit so that we have open terminals. And once we have open terminals, we will determine Req between those open terminals. You have R1, R2, and R3. Now here's where I talk about passive reference configuration, as well as the points about assuming the voltage polarities and the current directions. Okay, remember I said it'll make more sense when we come to an example. Well, this is that example. So this is the beginning of the analysis of our problem. We have no idea of the voltage polarities and the current directions that appear in the circuit. We do know that once we apply a voltage source, current will flow in the circuit, currents will flow through each of those resistors, and a voltage will appear across each one of those resistances, right? So let's begin here. Voltage source. Current always flows from positive to negative, high to low. But that's it for a passive component. That's the passive reference configuration. Current always goes from high to low. Current always goes from plus to minus. Okay. The only components we deal with in this course are, again, resistors, capacitors, inductors. All three of them are passive components. So current direction and voltage polarity for those components will always go from plus to minus. So if you're given a component, one end is plus, the other end is minus, the current is going from left to right, plus to minus. The flip side of that statement is that if you have a component and you're given the current direction, where's the plus? On the left or the right? On the left. Point of entry would be plus, point of exit is minus. Yes. Yes, so that's going to be the next point. So again, passive reference configuration applies to passive components like resistors, capacitors, and inductors. Current always goes from high to low, except when it's an active component like a source. If it's a source, whether it's a voltage source or a current source, current will go from minus to plus. It is supplying energy, it is supplying power. So again, power in real life is never negative. We put a minus sign in front of that to balance out our mathematical equations, right? Otherwise, our equations would never balance out. Law of conservation of energy. So if it's a source, then current goes from minus to plus. If it's a current source, so in this case, if it's a source, and I'm given the polarity like this, which direction is the current going, left or right? Towards the left. My current is going in this direction. If I was given a current source, where is the minus sign? On the left. So it'd be minus, plus. Okay, passive reference configuration states that for a passive component, current always goes from high to low, from plus to minus. Flip side of that statement is that if you're given a current direction, then the point of entry into the component is plus, the point of exit is minus. This applies to all passive components except for active ones like a source. A source, whether it's a voltage source or a current source, current will go in the opposite direction, which is minus to plus. Otherwise, our equations would never work. A battery is a source. Okay, battery is a source. This is constant voltage source. So you can say it's a voltage source. And a battery also, current goes from minus to plus. Is that clear to everyone? Again, fundamental concept. So let's apply this concept to our circuit. We have voltage source Vs on the left. Polarity for the voltage is already given to us. Which direction is the current flowing for the source? Is it going up or is it going down? It's going up, minus to plus. So current goes up. I'm going to label that as I. If you are driving a car around the circuit, that current, let's assume it's a vehicle. You're driving forward, you're not going backwards, right? Which direction is the current flowing through R1? Left to right or right to left? Logic dictates the current would follow this pathway, and there is nothing else in that path. So our assumption would be that the value for that current would be the same as I. So going back to last week, we make certain assumptions at the beginning of our analysis. The assumptions are based in logic. So the first step, the facts that are given to us in the problem is that we have a voltage source Vs with the polarity given to us as plus at the top, minus at the bottom. So current goes up in the circuit schematic. That same current has nowhere to go except through R1. So it has the same notation, it has the exact same value. Same current I that is being supplied by the voltage source also goes through R1. So R1, the current flowing through R1, is exactly the same as I. So I flows through the circuit, comes to this junction. Some of it goes down here. Some of it goes down here. Right? It splits into two. And the split values depend on the values of R2 and R3. Side note, one way to verify your answers, R2 is smaller than R3. So the current for I2, current I2 and I3, which one will be larger? I2 would be larger, or IR2, let's say IR2. The smaller the resistance, the larger the current. So when you solve a problem, that's another thing to keep in mind. It's an instant verification check. Combines back into I. Okay, let's go back to our REQ. Okay, REQ. The farthest end, R3 is in parallel with R2, which would then be in series with R1. Yes. Could be anything. Voltage, current, power, energy, could be anything. And that's what we're going to see here. Because once we have one value, so we have three quantities in Ohm's law: voltage, resistance, and current. In this case, we are provided voltage source Vs. Resistor values are given to us. We find the third quantity. Okay, so again, could be anything, no problem. So this is R3 parallel R2. 30 times 60 divided by 30 plus 60, 1800 divided by 90 gives me 20 ohms. Again, you can do this on the calculator, obviously, but you should get 30 ohms. So REQ is 30. Now I have one single source and one single resistance. I plug it back into the circuit and I have my three quantities. Apply Ohm's law, which is the second step. V equals IR, and I can determine the value of I. Okay, find the value of I. I is equal to Vs divided by REQ. 90 divided by 30. I is equal to 3 amps. Let's take a 10-second pause and let that sink in. Any questions? Okay. So once we have that I, we expand the circuit back up again. You can find the voltages for R1, R2, and R3. So once we have I, we know that the same current I flows through R1. Therefore, VR1 is simply equal to I times R1 30 volts. Makes sense to everyone? That's the voltage drop across the resistor R1. So we have the same current I going here. We determine that this is 3 amps. The 3 amps going into R1 causes a voltage drop of 30 volts. Voltage Vs supplies current, total current I. I has nowhere else to go except through R1. When it goes through R1, causes a voltage drop to appear across R1. Apply Ohm's law, and you can determine it as 30 volts. What is the voltage polarity? We just talked about it, right? For the resistor. For resistor R1, where is the plus? Is it on the left or the right? So the point of entry. So here, if a component has a current direction, and the current direction is known to us, point of entry is plus, point of exit is minus. So if current I is entering R1 through the left, then voltage polarity is plus on the left, minus on the right. Again, we are assuming the polarity, but it's based on logic. And same rules apply to the voltage across R2 and R3. Point of entry is top, so plus at the top, minus at the bottom. Okay. Now, R2 and R3 are combined into one single resistance, which is R4. Well, actually, didn't name it R4, but let's just note it as R4. Okay. R4 is not real, it's hypothetical. We combine it on paper, we know it is worth 20 ohms, right? It's a parallel combination. So we can find the voltage across this parallel combination of R2 and R3. We apply Ohm's law again. Or we can apply KVL, right? This circuit right now, actually I did not draw this here, but when you combine R2 and R3 together, this is R1, This can be R4. And this is where our power supply is connected. So I is going through R4 also. Make sense? Same current I. Physically, it's being split in two. But mathematically or theoretically on paper, we can say the same current I is flowing through R4. Again, R4 is the parallel combination of R2 and R3. So the same current I is flowing through that parallel combination. We see it as one. We calculate it as one single resistor. We apply Ohm's law again, and we can find the voltage across R4 as I times R4. 3 into, what was it, 20? 60 volts. You can also apply KVL. So if you apply KVL, you would get minus Vs plus VR1 plus VR4 is equal to 0. So VR4 is equal to Vs60 minus 30. Sorry, 90 minus 30. And you get 60 volts. Make sense? You can find it using KVL or you can find it using Ohm's law. Your choice. Yes. So you're talking about here? You can, because this voltage is a result of both of these resistors working together. So the 60 volts that appear, so in a parallel combination, we always say the voltage remains the same. But it's not as if, if 20 volts is appearing across 3 resistors, then we have 20 volts for all 3 resistors. If you remove one of the resistors from that network, then the 20 volts will change because the circuit has now changed. So any resulting voltage that appears across a parallel network of resistors is a result of all of those resistors working together. If you remove one or more resistors from that parallel network, now the network has changed, and so the voltage that appears also changes. So you have to keep that in mind. So when I was talking about KVL, we have 90 volts, 30 volts, and then the rest of the voltage has to fall across this point right here. That's it. So the larger technique or the larger method is series parallel analysis technique, but you can apply different techniques inside of it. So whether you use Ohm's law or whether you use KVL, you would still get full credit. Okay. So if a problem asks you to solve it using series parallel analysis technique, that is what you are going to show me. You take a large network of resistors, you reduce it down to one single resistance, and then you expand the circuit up again. Within that method, within that technique, you can use any technique you want. So does this make sense? Okay, and from this you can calculate IR1 and you can calculate IR2 and IR3. So apply Ohm's law again, and IR2 is VR4 divided by R2, which is 60 divided by, what is it, 30? 30. 2 amps. And IR3 is VR4 divided by R3. So 60 divided by 60. 1 amp. Which makes sense. 3 amps divided into 2, 2 and 1. Straightforward. About 5 minutes left. Okay, let's stop. Let's end class here for today, and we'll pick up here again on Friday. I will be here next week. Okay. And hold on.